Hello linear algebra students. This video lesson is on change of basis. Now below are three bases for R2. For each basis, express the vector v that originates at the origin and terminates at the indicated point as a linear combination of the basis vectors. So in this first example, the vector v in question is the vector that begins at the origin and ends at this point. And the basis we're using for R2 in this case is the collection of standard basis vectors. We have the vector 1, 0, which we call the I vector, and the vector 0, 1, which we call the j vector. These two vectors are indicated here and here. Now, the task is to find the linear combination of these basis vectors that will produce the vector v. We can see that if we do 4 copies of the I vector, that'll produce this green vector, and then we need to add to that 3 copies of the j vector. Add these two vectors and we get the orange vector v. Therefore, we can express the vector v as 4 copies of the I vector plus 3 copies of the j vector. And note that this basis, we're calling it b1, is simply the standard basis for R2. It forms a basis because the vectors I and j are independent of each other, and they span all of R2. Any point in R2 can be expressed as a linear combination of I and j. Now in this next example, we're using different basis vectors. The first one is 1, 1, which we'll refer to this as vector u sub 1. And then the second vector in this basis we'll refer to as u sub 2, and that's the vector 0, 2. And they are depicted in this image. Here's vector u1, and here's vector u2. Now, because these two vectors are linearly independent of each other, they too will also span all of R2. And any location in R2 can be described as a linear combination of these two vectors. We can see that if we do 4 copies of u1, that'll take us to a location directly above the point in question. But now we need to drop down to arrive at the point 4, 3, and so we have to do a negative scalar multiple of u2, and we have to cut the magnitude in half. So this red vector would be the negative 1/2 of vector u2. And this orange vector v can be constructed by doing 4 u1s minus 1/2 u2. Now let's look at basis 3. Basis 3, the two vectors, let's call them v1 and v2. They are linearly independent. They're not multiples of each other, and therefore they will span all of R2. So any point in R2 could also be represented as a linear combination of these two vectors. Now, if our goal is still to construct this vector v, then we need to determine what linear combination of v1 and v2 will produce this vector v. And this one is not as obvious as the last two. Imagining some sort of right triangle, I can anticipate that I might need to do a shorter version of v1. So I might need to scale down its magnitude, and then I might need an increased magnitude of v2 in order to combine the red and the green to produce this v vector. And in such a case, when it's not obvious how to scale the two vectors so that when added together we get the desired vector, we can simply create a system of equations and solve it. For example, we are trying to solve what multiple of the first vector plus what multiple of the second vector will equal the desired vector 4, 3. Well, this is simply solving a system of equations. It's equivalent to solving the following matrix vector multiplication. We put the basis vectors as columns of a matrix. We multiply by some unknown vector, c1, c2, and we want this to equal the result vector 4, 3. So we can put this in an augmented matrix and then row reduce to achieve this result. So this tells me that c1 has to be 9/10 and c2 has to be 13/10, which confirms our intuition that we had to decrease the magnitude of v1 but increase the magnitude of v2 in order to arrive at the point 4, 3. So our vector v can be written as 9/10 of the first basis vector plus 13/10 of the second basis vector. Okay, reading right here. For a basis b that equals some vector u1 up through vector un of Rn, the scalars ci such that vector v is equal to c1 u1 plus etc. up to cn times vector un are called the b coordinates of v, and are written v sub b is equal to, and you take those scalars and you make a vector out of it, and then you can put the subscript b next to that vector. So let's look at this second case using basis 2. So we can see that the vector v, in terms of that second basis, so I'll put subscript b sub 2, is equal to the vector 4, negative 1/2, suggesting we do 4 copies of the first basis vector and negative 1/2 copy of the second basis vector to arrive at vector v. Now, if we have the subscript right here, then that's really adequate. But if we want to go overkill, we can put that subscript on this as well. And we can also, of course, write this as a column vector. And again, we can put the subscript on this. This is simply identifying the scalars that we need on the basis vectors that are in B2 in order to arrive at vector v. In this third case, we would say that the vector v, but in terms of basis 3, is equal to the vector 9/10, 13/10. And we can put the subscript sub b3, and of course we could write this as a column vector as well. Now, it is a bit overkill to put the subscript b3 on all of these. If you have it in just one position, say here, then you don't need to write them here and here as well. But if you just have one of these out of context, then you want to put the subscript on that vector. So we know that we're referring to that these are the b coordinates given the basis b, whatever that basis is. Now, continuing to read right here, if the basis b contains the standard basis vectors in order, then the b coordinates are called the standard coordinates of v. And then moving forward, we will assume that v with no subscript implies the standard coordinates of the vector v. Looking at this first case, b1 contained the standard basis vectors in order. In such a case, we'll write v without a subscript, and the coordinates would be 4, 3. Or you could write this as a column vector 4, 3. And this is how we've been writing vectors up to this point in this course. So nothing new here. And no subscripts are required because by default, without a subscript, we will assume that 4 and 3 are the scalar multiples of the standard basis vectors I and j to arrive at our vector v. Now, I'd like to show you with technology what it means to do a change of basis. So looking here, we have the point 4, 3 and the vector that would connect the origin to that point. Now, the standard basis vectors are this blue and red vectors. And the grid that we're used to seeing here in the xy plane or in the R2 space is a rectangular grid that conforms to these standard basis vectors. Each block going to the right indicates how many copies of the blue vector we're doing, and each block going up indicates how many copies of the j vector or the red vector that we need. And so to arrive at the point 4, 3, we simply need to go across 4 blocks. So we would do 4 copies of the I vector and then go up 3 blocks and do 3 copies of the j vector to arrive at this location. But what if we change the basis vectors to these vectors? This was basis 2. Well, this grid no longer feels relevant, and so we want to hide the grid and replace it with a new grid in terms of these basis vectors. And if the goal is still to arrive at this location, then we have to ask ourselves, well, how many blocks, and these are parallelogram blocks, or how many copies of vector blue do we need to get directly above this vector 4, 3? And we can see we would need to do 4 copies of the blue to arrive right here. And since vector u2 points up, we need to go negative 1/2 of that vector to arrive at this location. But we create this new skewed grid based off these 2 basis vectors that we are using to describe this location. 4 copies of the blue and then negative 1/2 copy of the red. And in basis 3, making a grid using them, we can see that we would not need to go the entire length of the blue. In fact, we only have to do 9/10 of it, and then we would have to go in the parallel direction to the red more than 1 copy of red. In fact, it turned out to be 13/10. So 9/10 of the blue plus 13/10 of the red is what it took to arrive at this location, given this new grid. Okay, let's go to the next page. Below are 2 bases for R3. For each basis, find the b coordinates for the vector v equals 3, negative 1, 5. Now, the first case, basis 1 is just our standard basis. It contains the standard basis vectors and in order, those vectors being I, j, k. So as we've done in the past, we can simply say that vector v is equal to, we need 3 copies of I negative 1 copy of j, and 5 copies of k. And this basis is the standard basis for R3. So we can take those coefficients and make a vector out of them. So we have 3, negative 1, 5. Really is just repeating what was already given up here. But now B2 is a new basis for R3. We can prove that this is a basis by constructing a matrix with these vectors as its columns, and then finding the determinant. And you would see that the determinant is non-zero, meaning that these three vectors are independent of each other. So they do form a basis that will span all of R3. Let's call the vectors U1 through U3. And once again, the goal here is to solve the following system. What scalar times U1 plus what scalar times U2 plus what scalar times U3 will produce the desired vector V? Well, this can be rewritten as a system of equations in matrix form. Put the vectors U1, U2, U3 as the columns of the matrix. Multiply this by an unknown vector, C1, C2, C3. And set this equal to the desired vector, 3, negative 1, 5. So we'll convert this to an augmented matrix, and then use technology to put this matrix in reduced row echelon form. This tells us that C1 needs to be 5, C2 needs to be negative 1, and C3 needs to be 2. Thus, vector V can be written as 5 copies of U1 minus 1 copy of U2 plus 2 copies of U3. Thus, this vector can be written in terms of this new basis, B2, and its coordinates would be these three scalars, 5, negative 1, 2. And this is with respect to basis 2. Or you could write it this way. Okay, let's go to the next page. Below are two bases for R4. For each basis, find the B coordinates for the vector V equals 2, negative 3, 4, 0. Well, B1 is the standard basis for R4. Now, the labeling of these vectors, we get away from the IJK labeling, and we switch over to a new labeling for basis vectors you will see in some textbooks. This first vector is often labeled as vector E sub 1, and then we have vector E sub 2, vector E sub 3, and vector E sub 4. So E's are often used to represent standard basis vectors, and we could also do that for R3 and R2 instead of the IJ and IJK notations. But these are the 4 standard basis vectors for R4 in order. And to construct vector V, we simply have to do 2 copies of the first one minus 3 copies of the second basis vector plus 4 copies of the third basis vector, and then we don't need any copies of the fourth basis vector. And of course, this gives us the coordinates 2, negative 3, 4, 0. These are the standard coordinates, and they of course match these up here. We expect no change when you're working with the standard basis vectors. But now let's take a look at B2. These 4 vectors do span all of R4. They are linearly independent. If you construct a matrix with these vectors as its columns and find the determinant, you will get non-zero, meaning that they are independent of each other. And once again, our goal is to solve the following system. What scalar multiple of the first vector, and let's call these vectors U1 through U4. So what scalar multiple of the first vector plus what scalar multiple of the second vector, etc., will equal the vector V. Converting this to a system in matrix form, we get, which we then convert to an augmented matrix, which we now put in reduced row echelon form. This gives us C1 through C4, and we can now express vector V as a linear combination of these basis vectors. We'll have 9 halves of the first basis vector, minus 1 copy of the second basis vector, minus 1 half of the third basis vector, and then minus 1 half of the fourth basis vector. So the coordinates of V, but with respect to this basis, B2, are 9 halves, comma, negative 1, comma, negative 1 half, comma, negative 1 half. Again, with respect to basis 2. Okay, let's go on to the next page. Now suppose the columns of a matrix A form a basis B of Rn. Given A and the b coordinates for any vector, the standard coordinates of the vector are found as follows. Okay, so let's say that we have the b coordinates of a vector, and let's say those coordinates are C1 through Cn. And then the basis is the set vector U1 through vector Un. This tells us that the vector v was constructed from this basis by doing C1 times vector U1, etc., up until Cn times vector Un, which we factor as a matrix vector product. Columns of the matrix are the basis vectors, multiplied by a vector of the coefficients, which is the matrix we're calling A, times the b coordinates of this vector. So in order to arrive at the standard coordinates v, we simply have to do this product. In other words, just do this linear combination of the basis vectors to figure out what the standard coordinates are for this vector. For each basis b, find the standard coordinates of the indicated vector, which is expressed using its b coordinates. If the basis vectors are these two vectors here, and the b coordinates for the vector v are negative 2, 4, this simply means do negative 2 of the first basis vector plus 4 of the second basis vector. That will tell us what the standard coordinates of this vector are. Or simply, we can do matrix vector multiplication. So to arrive at the standard coordinates, we do matrix A, which will be constructed by putting the basis vectors as its columns, times the vector that's composed of the b coordinates. So the matrix A, first column will be 3, negative 1, second column will be 1, 3, and multiply that by the vector negative 2, 4, and do this matrix vector multiplication, which can be thought of as doing negative 2 times the first column plus 4 times the second column, and we arrive at the vector negative 2, 14. And these are the standard coordinates. So this vector v would be go left 2 units and then go up 14 units. So looking at this example with our technology, our basis vectors are the blue vector and the red vector. And the b coordinates for the vector in question are negative 2, which means do negative 2 of the blue vector, and then 4, which means do 4 of the red vector. So we would basically go left 2 in this grid, and then go in the same direction as the red vector, 4. And that takes us to this location right here. Well, in standard coordinates, that is the location negative 2, 14. In here we can see both grids at the same time. So using standard coordinates, I would go left 2 and then up 14 to arrive at this location. But using the new basis vectors, I would go the opposite direction of blue, but 2 copies, and then 4 copies in the direction of red. And that takes me to the same location. Okay, repeating this, now we have this basis of R3, and the b coordinates are negative 1, negative 2, negative 3. So to find the standard coordinates, we simply have to create a 3 by 3 matrix constructed using the basis vectors, and then multiply that by the b vector. And this gives us the coordinates negative 4, negative 2, negative 2. And these are the standard coordinates. And in our third case, we had a basis for R4, and its b coordinates are 1, negative 1, 0, 2. So doing this linear combination of these basis vectors amounts to doing matrix vector multiplication, which when we compute, we get 1, 7, 1, 2. All right, moving on to the next page. Again, suppose the columns of a matrix A form a basis B of Rn. Then A is square and invertible, and we can find the b coordinates of any vector v as follows. So we already know that if I want to find the standard coordinates, I simply do the product of the matrix A, whose columns are the basis vectors of b, multiplied by the vector in terms of that basis. But if I'm trying to find the b coordinates of this vector, that means I'm looking for this part of our equation, then I would simply multiply this equation on the left by the inverse of A. And this product here would be the identity matrix. Thus, we effectively isolate the b coordinate vector. So we get the b coordinate vector can be calculated by doing the inverse of A times the standard vector, the vector whose coordinates are the standard coordinates. So these three examples here, for each basis, find the b coordinates of the indicated standard vector. We've already done these three, but we did it by solving systems of equations by using reduced row echelon form. So this first one, if I back up to page 1, we solved this system right here. So I'll copy and paste this right here. This was the system that we solved in order to arrive at the b coordinates for this basis. And before we used an augmented matrix and put this in reduced row echelon form, but now I'm just going to solve the system using an inverse matrix. So this is our coefficient matrix A, we're saying, and to find C1, C2, which are the b coordinates of this vector, I simply need to do A inverse times the standard coordinates. I calculated the inverse of this matrix using technology. Its entries are 3/10 and 1/10 for the first column, and -1/10 and 3/10 for the second column. Multiply this by 4/3, and we get 12/10 minus 3/10, that's 9/10, and 4/10 plus 9/10, that's 13/10. And this, of course, is the same result when I did it the first method by using a reduced row echelon form of an augmented matrix. Similarly, we can repeat the findings for the next two cases, but by using inverse matrices instead. So the b coordinates of this vector will be equal to the inverse of the matrix whose columns are the basis vectors times the standard vector. Using technology to get the inverse, we get the following. And then multiply that inverse matrix by the standard vector, and we get the following vector of b coordinates: 5, -1, 2, confirming our results from earlier. And then in our last case, the b coordinate vector is equal to the product of the inverse of the matrix A, whose columns are the basis vectors. Here is A, and we must find its inverse, and then multiply that inverse matrix by the standard vector, to -3, 4, 0. Using technology to get the inverse, we get this matrix with lots of fractions. And if I were doing this by hand, I might recommend you factor out the least common denominator from this inverse matrix. So factoring out a 1/8 of that inverse matrix, we get a matrix of integers, and it's easier to multiply this matrix and this vector and then do 1/8 of our answer. So we'll have 1/8, and the result of this matrix vector multiplication is 36, -8, -4, -4. And then I can do 1/8 of all of these entries, and I get 36/8, which is 9/2. Then we get -1, -1/2, and -1/2. And this confirms the answer we got on an earlier page. Okay, moving on to the next page. This page is about how to convert from the b coordinates for one basis to the b coordinates of a different basis, where neither of the bases are the standard bases. So let the columns of A1 and A2 form two different bases, B1 and B2, of Rn. Then we can convert between the B1 coordinates and the B2 coordinates of a vector, as shown below. So we know that in each case that the standard coordinates V can be found by multiplying the matrix A1 times the B1 coordinates for that vector, or we can arrive at the vector in standard coordinates by doing the product of A2 times the B2 coordinates of that vector. Both of these calculations can produce the standard coordinates. Well, this tells us that these two expressions should be equal to each other. So we have A1 times the B1 coordinate vector must be equal to A2 times the B2 coordinates of the vector. And depending on which basis coordinates I'm looking for, I will manipulate this equation in different ways. For example, if I'm trying to isolate the B1 coordinates of the vector, then I would multiply both sides of the equation on the left by the inverse of A1. So I would have A1 inverse times A2 times the B2 coordinates vector. But if I was looking for the B2 coordinates vector, then I would multiply both sides of this equation on the left by the inverse of A2. So I would get A2 inverse times A1 times the B1 coordinate vector. All right, so given the two bases of R3 below and the indicated vector, express the vector in terms of the other basis and in standard coordinates. So we have the vectors that are in both bases. Hence, we know the matrices A1 and A2. A1 would be, and matrix A2 would be. And we're given the B1 coordinates of the vector. So we're looking for the B2 coordinates of the vector. So I'm going to use this formula in particular. So the B2 coordinates of the vector can be found by doing the inverse of A2 times the matrix A1 times the B1 coordinates of the vector. So I use technology to find the inverse of A2, then multiply by A1, then multiply by the B1 coordinates. So you could do this a variety of ways. You could first do this matrix vector multiplication and get a vector, and then multiply by the inverse matrix. Or you can multiply the matrices together first to get a new matrix, and then multiply by the B1 coordinates. I'll go ahead and multiply the two matrices together first, producing this 3 by 3 matrix, and then multiply by the B1 coordinates. And in the end, this gives us the vector -1, 1/2, 5/2. Now, had I done this product first, that would have produced the standard coordinate vector, which is basically doing this formula right here. And this product gives us 3, 3, 7. So in summary, we have that the vector in question in standard coordinates is 3, 3, 7. So that's basically 3 i's plus 3 j's plus 7 k's. And in terms of the other bases, we can write this vector as 2, 3, -1, but that's in terms of the first basis. Or we can write this vector as -1, 1/2, 5/2, but that's in terms of the second basis. I'll leave it to you to confirm that the linear combination specified here of the two bases both will produce the vector 3, 3, 7 in standard coordinates. And this concludes our lesson on changes of basis.